So there are a bunch of concepts we'll cover as part of the physical layer. This is the first in the series, but first let me see how much you remember and how good you are at solving riddles. So the role of the physical layer is bit by bit delivery as captured by this figure. So we want to move data in the form of bits between two neighboring nodes over a link. These nodes could be hosts, routers, or switches. In case of hosts, these are typically general purpose computers where some portion of the functionality is implemented in software and some in hardware. But if it were routers and switches, a lot of the functionality is implemented in hardware for performance reasons, for example, high speed. To achieve bit by bit delivery, we need to tackle the following. So I'm going to cover the following concepts as part of the file layer. First, we will look at the components that make up file layer. What are these? Right, a node and a link. Next, we will look at some theory behind file layer. Spectrum of signals, what is the maximum data rate you can get out of a link, so on and so forth. Next, we will look at data transformation, basically how to convert bits into signals. And in encoding, we will cover a few popular data transformation techniques, for example, like the ones that are used in Ethernet. So we need to cover all these to understand the operation of the file layer, but in this video, I'm going to look at just this aspect, components. Within components, here is the outline. First, we will look at the internals of a node, specifically a host. Then we will look at the characteristics of a link and also the different types of links. Moving on to host internals. Assuming the node is a computer, let's see how it looks inside. Now, looking at this figure, I know you have this urge to open up your computer. By all means, go ahead. But if anything goes wrong, I'm not to blame. So in this figure, what is of interest to us is this area. This is where the network adapters go. This is an example of an Ethernet adapter, and this is a wireless adapter. So you plug them into these slots. So if you didn't open the computer, what you will see is an Ethernet jack through which you plug in Ethernet or an antenna sticking out. So that's hardware. In terms of software, most of the applications like email, web, or file transfer protocols, these are implemented at the user space as processes. So this is where they are implemented. And the actual protocols as such are implemented at the kernel space. So this in turn is organized in this fashion where the socket layer acts as an interface between the application processes and the protocol. Finally, the data arrives at the interface layer, which includes the device drivers. For example, Ethernet driver or Wi-Fi driver, and these drivers put the data onto the physical media. So if you've done a course on computer architecture, you would have already seen this block diagram. What is of relevant to us here is the network adapter. We have already seen pictures of the Ethernet adapter or the Wi-Fi adapter. This is a piece of hardware. Often this implements a processor as well. The data as such resides in the memory, and when you want to transfer this data over a link, it has to be moved into the network adapter. And similarly, when you're receiving data from a link, you want to move the data back into the memory. There are two ways to move the data. One is called the direct memory access. In this case, the adapter directly reads and writes into the host memory. Another is programmed input-output. In this case, the CPU plays a role. In other words, it is responsible for moving the data between the adapter and the memory. Moving on to links, another important component at the physical layer. We have already seen many of these links. That Ethernet cable that you plug into the computer is an example of twisted pair. The cricket matches that you watch on cable TV is thanks to coaxial cable. So cable TV uses these cables. and that thing in the pocket that you can't live without makes use of wireless. So a link is nothing but a physical medium that propagates signals, and signals are nothing but electromagnetic waves. Now, when I mention a wave, your physics background should flash this equation in your head, where the speed of light in the medium is given as the product of the frequency and wavelength of the wave. Typically, you are aware of this number. This is the speed of light in vacuum or free space, but typically in some of the copper wires or this coaxial cable, the speed of light is a lot lesser, ranging from 2 into 10 to the power of 8 to 3 into 10 to the power of 8. For example, in coaxial cable, it's only about 60% of the speed of light in vacuum. So these physical media, unfortunately, are not very perfect. They tend to do things to the signals which you wish rather they didn't. So a signal can often be thought of as a summation of electromagnetic waves of different frequencies, and as the signals propagate through a media, they experience many things, one of which is attenuation. So basically, as the signal propagates, it loses energy over distance, and this is expressed in decibels per kilometers. So first, let's see what I mean by decibels. So this is basically the ratio between two power quantities expressed in a logarithmic scale. So 10 log 10 P1 by P2. So if I say 3 decibels, that means 3 is equal to 10 log 10 P1 by P2, which implies P1 by P2 is 10 to the power of 0.3, which is roughly equal to 2. In other words, the power reduced by half after 100 meters. That means it suffered a 3 dB loss after 100 meters. So another thing to note here is that the different frequencies of the electromagnetic waves experience different amount of loss. So often some frequencies are fully attenuated, leading to what is called a link bandwidth. So this basically captures the range of frequencies that suffer little attenuation. Another thing the signals can experience is what is called delay distortion. This happens because the different frequencies propagate at different speeds. So what this basically means is they do not arrive at the receiver at the same time. These media can also experience noise. So for example, thermal noise could be due to random motion of electrons within the media itself. And they can also experience crosstalk because of interference from adjacent transmission. So this figure will show you why crosstalk can happen. As you can see, multiple strands of wires are packed within the same cable, and transmission in this wire could interfere with transmissions in this wire. So the end result of all this is the received signal can be quite distorted. Let me show an example. Suppose you were to send this particular square waveform through a medium, what you will receive is represented by this. As you can see, it is very squiggly because of the noise, and the attenuation as well as delay distortion widens the particular pulse. So this is a pulse which got widened because of the attenuation as well as the delay distortion. So here is a picture of the electromagnetic spectrum that shows waves all the way from 1 Hertz to 10 to the power of 24 Hertz. Typically, communication happens only within this range. Beyond this range, like X-ray and gamma rays are very difficult to produce and embed information within these waves. And not only that, they are also dangerous to humans. So within this communication range, you have here, it also shows the media, what kind of frequencies it supports. So for example, the twisted pair cable supports frequencies between 10 to the power of 4 to about 10 to power of 8. In other words, any frequency above this gets severely attenuated. You can't pass those frequencies through twisted pair. And similarly, coaxial cable from 10 to power of 5 to roughly about 10 to power of 9, and fiber optic cables support very high frequencies from 10 to power of 14 to 10 to power of 15. In terms of wireless, it can support a whole range of frequencies, but typically some portion of this band is allocated for specific purposes. So for example, the frequency band here has been allocated for FM radio. The frequency band here has been allocated for AM radio, and the frequency band here is allocated for TV, and here for satellite, so on and so forth. So let's quickly see some of the popular links. The twisted pair links is used in Ethernet as well as telephone lines. There are different categories here, Cat3, Cat5, Cat6. The categories are a function of how many twists you have per centimeter, as well as some inductance between the pairs and so on and so forth. So what is of relevant here is this, where this is the bandwidth of the link and this is the attenuation. So for example, Cat5 links have a bandwidth of about 100 megahertz and suffer attenuation between 2 to 24 decibels per 100 meters. Now, why do you think this is a range? This is because different frequencies suffer from different attenuations. So lower frequencies suffer less attenuations, whereas higher frequencies suffer more attenuations. Typically, these cables are used under 100 meters. Why? We'll see the reasons for it shortly. And they support data rates between 10 megabits per second all the way to 1 gigabit per second. So next is coaxial cable. It's typically used in cable TV. It can provide up to 1 gigahertz bandwidth. And these also suffer attenuation ranging from 1 to 45 decibels per 100 meters, but for any given frequency, coaxial cable suffers less attenuation than twisted pair. These are used up to 500 meters and they provide data rates between 10 to 100 Mbps. Fiber optics are used in long haul transmissions. These are what form the internet backbone. They support frequencies that are in terahertz and their attenuation is extremely small, which is 0.2 decibels per kilometer. Remember earlier I was saying per 100 meters, whereas this is per kilometer. And they can go for long distances, tens of kilometers, and they can support extremely high rates up to 10 gigabits per second. So in terms of wireless, there are a whole range of usage: TV, satellite, cellular, Wi-Fi, WiMAX, so on and so forth. And spectrums can range from a few kilohertz to few hundred gigahertz. But actual allocated spectrum is a function of technology. For example, for Wi-Fi, 40 megahertz is used for transmission purposes. And for LTE, which is the cellular, advanced cellular technology, 20 megahertz is used for a particular transmission. And how much attenuation they suffer, naturally this is going to be a function of the buildings, the trees that block the propagation of the waves. But if it were free space where there is no obstruction, this is a formula that gives the loss they suffer as a function of distance. For example, at 1 kilometer and 100 megahertz, the loss is about 74 decibels after 1 kilometer, and similarly at 1 gigahertz the loss is about 94 decibels. You can cover distances from a few meters to few kilometers, and the data rates you can support are range from few this should have been few kilobits to hundreds of megabits per second. So links are also classified based on how they support data flows. For example, full duplex links support data flow in either direction. This they achieve mainly through using two pairs of wires, one for each direction. Half duplex links support data flow in only one direction at a time. The way you can relate to this is through a walkie-talkie. In walkie-talkies, you talk, stop, and then provide an opportunity for the other person to talk. In other words, two people cannot talk at the same time. Now in simplex links, you support unidirectional communication permanently. In other words, you cannot have data flow in from the other direction. This is not permitted. You only permit data flow in only one direction. The way to relate to them is through a one-way street. So a quick summary of what we have seen in this video. There are two components at the physical layer. One is node, another is link. Within a node, we looked at the hardware, how the software is organized, and how we move data from the memory to the adapter. We also studied about links, which basically carry electromagnetic waves. We saw how links can be imperfect, they can attenuate, they can cause delay distortion, they introduce noise. And we also looked at spectrum, that is the bandwidth of these links, and also studied different types of links: twisted pair, coaxial cable, full duplex, half duplex, so on and so forth. So going ahead, we will see how we can transform the data to signals which are in turn carried by these links.